I want you to picture this scene with us. It's May 7th, 1942, Washington, D.C., deep inside the Navy's Bureau of Aeronautics. And the mood in that room, well, it wasn't just tense. It was thick with failure, almost desperation.
You had Bill Schwendler there, a lead engineer from Grumman, and the papers he was holding, they weren't routine reports. They were combat accounts coming back from the Pacific.
And they read, quite starkly, like obituaries, stacks of them.
Yeah, they were the brutal confirmation of what the Navy already feared, a full-blown air crisis. Our pilots flying the F6F Hellcat, I mean, it was a tough plane, but it was being systematically taken apart by the Japanese Zero.
It wasn't about pilot skill, was it? It was just the machine couldn't keep up.
Exactly. The Wildcat, it was rugged, sure, built like a tank, but it was slow, and its climb rate, terrible. Against the Zero, especially up high, our guys were just outmatched.
Schwendler had the numbers right there. The F6F Wildcat, its top speed was maybe 318 miles per hour.
And the Mitsubishi A6M Zero, it could push 331, maybe even a bit more under the right conditions.
13 miles per hour. Doesn't sound like much on paper.
But in a dogfight at 20,000 feet, that 13 miles per hour was everything. It was the gap between breaking away and becoming another name on that casualty list Schwendler was carrying. It was life and death, plain and simple.
Okay, so crisis point, utter crisis. And this is where the story takes this almost unbelievable turn. The Navy looks at Grumman and basically says, fix this. Give us a fighter that can beat the Zero.
Not just a fighter, a dominant fighter.
Right. And here's the kicker. You need to design it, test it, and get it into mass production in 16 months.
16 months.
Yeah.
Just let that sink in for a second. Think about other iconic planes of the war.
Yeah.
The P-51 Mustang, legendary plane, right? That took about 3 years from concept to being fully operational.
Yeah.
The British Spitfire, even longer, maybe 4 years of development.
So 16 months wasn't just ambitious. It was bordering on insane.
Absolutely. And this wasn't, build us a prototype and we'll see. The Navy needed planes, hundreds, then thousands, rolling off the line while the design was still being tweaked based on combat reports.
Mass production from basically day one.
While still designing it, it was a monumental gamble. The stakes couldn't have been higher. Control of the skies over the entire Pacific Ocean. Every day past that deadline meant more losses, more territory falling.
So how on earth did they pull it off? That's what we're diving into today. The incredible story of the F6F Hellcat. We're going to look at how Grumman managed this feat, blending this almost Depression-era frugality with some really radical production ideas.
And a relentless focus on what the pilots actually needed. That feedback loop was critical.
Absolutely. We'll trace how this plane went from a desperate requirement to the machine that achieved that staggering 19-to-1 kill ratio and completely changed the game in naval aviation. From crisis to dominance. Okay, so to understand how Grumman moves so fast, you have to start with the company culture and the guy at the top, Leroy Grumman. They had this nickname, didn't they?
They did. Grumman Iron Works. And it wasn't just a catchy phrase, it summed up their entire philosophy. They built carrier aircraft, and carrier aircraft needed to be tough, really tough.
Able to take a pounding on landing, absorb battle damage.
Exactly. Survivability and ruggedness often came before cutting-edge aerodynamics. Their planes might not have always been the fastest or prettiest, but the pilots trusted them. They knew a Grumman plane would likely get them home. It was about dependability under extreme stress.
And Leroy Grumman himself, he wasn't just an engineer. He'd steered the company through the Great Depression. That must have shaped how he approached this contract.
Oh, profoundly. That Depression-era experience taught them that panic costs money and complexity costs time and money. Grumman survived by making every rivet count, both literally and figuratively. Every design choice had to be efficient, practical, easy to build.
So that thriftiness became a kind of secret weapon for the Hellcat project.
It really did. While maybe other companies were dreaming up complex, elegant designs, Grumman, under Bill Schwendler, took a hard look at the Wildcat and asked, what absolutely needs to change and what can we keep simple? They simplified everything that wasn't directly related to beating the Zero.
Simplicity as a core principle.
Yeah.
How did that translate into the actual hardware?
Well, take the landing gear. Lots of fighters back then had these really complex, multi-jointed systems to fold the gear perfectly flush for minimal drag.
Right.
The Hellcat, it used a much simpler, incredibly robust system. The wheels basically just retracted straight back into a bulge under the wing. Yeah, maybe it added a tiny bit of drag, but it was fast to build, almost unbreakable on hard carrier landings, and easy to fix.
And the cockpit, that's another great example. They didn't reinvent the wheel there.
No, they pretty much lifted the entire layout straight from the F4F Wildcat, and that was genius operationally. The Navy needed pilots flying combat missions, not sitting in classrooms learning a whole new set of instruments and controls.
It drastically cut down retraining time.
Exactly. Pilots transitioning from the Wildcat felt instantly familiar. It was about getting effective pilots into effective planes as fast as humanly possible. Same idea with the wing, a straightforward, low-mounted design. Easy to manufacture, strong, and crucially easier for carrier deck crews to patch up if it took damage.
Which brings us to this idea of repairability. Schwendler's rule, they called it.
Yeah, Schwendler's gospel almost. Two parts to it. Every component should ideally serve multiple purposes if possible, but even more critical, everything had to be accessible.
Accessible under wartime conditions, right? Not in a nice, clean hangar.
Precisely. You have to remember, repairs weren't happening in San Diego. They were happening on a pitching carrier deck, maybe in the North Atlantic, freezing cold, middle of the night, bombs possibly falling. Schwendler famously insisted that things like hydraulic lines and wiring harnesses had to be routed where, and I quote, a 19-year-old mechanic with frozen fingers could get at them with basic tools at 2 a.m.
So the design wasn't just about function, it was about maintenance under the worst possible conditions.
That was the acid test. Schwendler would ask his engineers about a complex system. Can a crew chief fix this with a wrench and a screwdriver? If the answer was no, the design went back. Simplify it. Make it accessible.
And that had a huge impact on operational readiness, didn't it? Planes came back shot up, but got fixed fast.
Hugely. Hellcats often limped back looking like Swiss cheese, but because they were designed for field repair, they weren't write-offs. They could often be patched up and flying again in 48 hours. That kept more planes in the fight.
Okay, so simple, rugged, repairable design. But how did they actually build them fast enough? That 16-month clock was ticking.
That's where the modular design came in. It was key. The F6F wasn't conceived as one single structure built from start to finish. It was broken down into major subassemblies.
Like building blocks.
Sort of. You had the nose section built in one area, the center fuselage in another, the tail section, the wings, all being constructed simultaneously in different parts of the factory.
Wow, so parallel processing. Like Henry Ford's assembly line, but for a complex warplane.
Exactly. It allowed different teams to work on different parts at the same time without getting in each other's way, and the crucial advantage was flexibility.
How so?
Let's say combat reports came back saying the engine mount needed strengthening. With the modular design, they could incorporate that change into the nose section assembly line without stopping the production of fuselages or wings further down the line.
So they could evolve the design in real time without halting deliveries.
Precisely. The changes were phased in. The Hellcat was literally being improved while it was being mass-produced. That's how they hit that deadline. It was a constantly evolving machine right from the start.
Okay, so the philosophy is set, the factory is ramping up, but then comes the first big test. June 26, 1942, the prototype, the XSX-F1, makes its first flight. Bob Hall is the test pilot.
Yep, and it's got the Wright R2600 Cyclone engine, about 1,700 horsepower. Decent engine.
Hall lands. What's the verdict?
Well, diplomatically put, the feedback was not good enough. It was faster than the Wildcat, sure, tougher, handled well. But crucially, it still wasn't significantly faster than the Zero where it mattered most, up around 20,000 feet.
The engine just couldn't breathe up there.
Pretty much. It gasped for air, as the engineers put it. At altitude, the performance dropped off. It didn't have that decisive edge they desperately needed. This was a major crisis moment.
Because changing an engine midstream, that's like ripping out the foundation of a house after you built the first floor, right?
Yeah.
Especially with that 16-month deadline limbing, 4 months were already going up.
It's a program killer usually. Massive redesigns needed. Cowling, engine mounts, fuel lines, center of gravity calculations, everything changes. There must have been some serious high-stakes meetings at Grumman right then.
But Leroy Grumman made the tough call.
He did. He understood the mission. A Hellcat that couldn't dominate at altitude was useless. He greenlit the switch to the Pratt & Whitney R2800 Double Wasp.
The Double Wasp. Now, that was a beast of an engine.
Oh, yeah. A proven, reliable 2,000 horsepower. A significant jump. But it wasn't a simple swap.
Bigger engine, heavier.
Yep, about 200 pounds heavier, which is a lot in fighter design. Normally, you'd fight tooth and nail to avoid adding that kind of weight.
But the trade-off was worth it.
Absolutely, because that extra 200 pounds bought them not just 300 more horsepower, but the real prize. The R2800 came with a sophisticated two-stage supercharger. That was the game changer.
Okay, explain the supercharger tech. Why was two-stage so critical against the Zero?
Right, so think about air density. As you climb, the air gets thinner, less oxygen for the engine. A supercharger is basically an air pump, forcing more air into the cylinder so the engine can maintain power.
Standard stuff on many planes.
Yes, but the Zero had a relatively simple single-stage blower or just relied on ram air. Its power fell off dramatically above, say, 15,000 feet. The R2800's two-stage system used two compressors, often driven by exhaust gases, to really compress that thin, high-altitude air. It tricked the engine into thinking it was still flying much closer to sea level.
So the Hellcat engine wasn't losing power at altitude.
It was actually optimized for high altitude. It performed best exactly where the Zero started to struggle. This flipped the entire performance equation.
And the results were immediate.
Astonishingly fast turnaround. They made the decision, re-engineered the prototype, and just 34 days later, on July 30th, 1942, the F6F with the R2800 took flight.
34 days.
Incredible, isn't it? And the performance leap was huge. Climb rate went from around 2,600 feet per minute to over 3,500.
Wow.
Top speed at altitude jumped past 380 miles per hour. Now it was decisively faster than the Zero in that critical combat environment.
And this gave pilots that zoom climb capability.
Exactly. Get into trouble. Don't try to turn with the Zero. Just firewall the throttle, nose up slightly, and use that massive power advantage to climb away, converting speed back into altitude. Escape, reposition, re-engage from above. It negated the Zero's main advantage.
The Navy must have been thrilled.
They authorized full-scale production right then and there. Even before all the exhaustive testing was done, they saw the potential. But packing that huge, powerful engine in there wasn't without its own problems.
The catch. What was it?
Heat? That R2800 generated an enormous amount of heat. Keeping it cool, especially during sustained climbs or combat, was a major engineering challenge. Overheat the engine, and you lose power, or worse, it catches fire.
So how did Grumman solve that? More elegant engineering.
Not exactly elegant, pragmatic, very Grumman. They basically had to enlarge the engine cowling significantly, made the whole front end of the plane bulkier, added more cooling gills, more openings to ram air through the engine cylinders.
Which led to that infamous description.
Yeah, the flying beer keg. It wasn't sleek, it looked powerful, maybe even a bit brutish, but it worked. It kept the engine cool, it delivered the power, and it didn't compromise the ruggedness. Function over form, every single time. That was the Hellcat.
Okay, so design locked, engine chosen. Now the production miracle. We're talking January 1943. The Grumman plant at Bethpage, Long Island. It's described as organized chaos. 25,000 workers.
And you got to remember who these workers were. 6 months earlier, many of them had literally never set foot in a factory. They were teachers, clerks, farmers, housewives, suddenly tasked with building one of the most advanced fighter planes in the world.
The training challenge alone seems insurmountable. No time for long apprenticeships.
No time at all. So Grumman basically applied the Detroit assembly line model, but took it to an extreme for aircraft. They broke down every single job, riveting a specific panel, wiring a particular harness, installing one component into incredibly simple, repeatable steps.
Simple enough to learn in a week.
That was the goal. Intense specialization. You didn't need to know how the whole plane worked. You needed to master your one specific task perfectly and quickly.
Describe that assembly line. How did it flow? How did they keep up the pace and the quality?
It was a moving line, very regimented. Each developing airframe spent a precise amount of time at each station. Station 1, install the main engine bearers. Station 2, lower the massive R2800 into place. Station 50, final systems checks and ground run-ups. Everything timed.
And the key was that if one station fell behind,
the entire line stopped. Instantly. No exceptions.
Wow, talk about pressure. Peer pressure built right into the system.
It was genius, really. It meant bottlenecks were identified immediately. If Station 12, maybe installing the wing root fairings, was consistently taking 5 minutes too long, it wasn't a problem for a meeting next week. It was a crisis right now.
And management or engineers would swarm the problem.
Instantly. They'd be down on the floor that afternoon. Was it a tooling issue? Did the workers need a different jig? Was the process sequence wrong? They'd figure it out and fix it, often within hours. Maybe provide a better pneumatic rivet gun or change the order of assembly slightly. Problems got solved immediately to keep the line moving.
And a huge part of this workforce, nearly 40%, were women, the Rosie the Riveters. They weren't just doing simple tasks, were they?
Absolutely not. They excelled particularly at the intricate, detailed work, things like wiring the complex instrument panels, installing hydraulic lines in tight wing spaces, handling the fine assembly work that required real dexterity and focus.
There's that amazing story about Doizadi.
Yeah, she's legendary. She's credited with assembling the leading edges for 847 Hellcat wings without a single rejection from quality control. That's just incredible precision day after day under wartime pressure. It shows the dedication and skill level this supposedly inexperienced workforce achieved.
So what kind of pace did they hit?
By mid-1943, it was truly staggering. They were rolling out 14 completed Hellcats every single day.
14 a day.
Think about that. That's roughly one brand new F6F coming off the line every 103 minutes, around the clock, 7 days a week.
How does that compare to other major aircraft programs?
Well, the famous B-17 Flying Fortress, a huge national priority, peaked at about 15 per day. But that was pooling the output of multiple giant factories: Boeing, Lockheed, Douglas. Grumman was doing nearly that volume just at Bethpage with the Hellcat. By the end of 43, they'd delivered over 2,500 Hellcats. The scale was immense.
But with that speed and that rapidly trained workforce, how did they prevent defects? A fighter isn't a car. One bad rivet can be fatal.
That inherent Grumman simplicity helped. Fewer complex parts meant fewer things to go wrong. But their quality control was also incredibly rigorous. It had to be.
What did they do specifically?
Famously, they practiced destructive testing. Roughly every 10th aircraft off the line was pulled aside, not for flight testing, but to be literally torn apart.
They destroyed a perfectly good brand new fighter.
Yep, they'd stress the wings until they broke, dissect engine mounts, check welds, measure tolerances, inspect every critical component for hidden flaws or material defects. It was a brutal but effective way to ensure the ones that did get delivered were absolutely sound.
And the results showed that worked.
Phenomenally well. The Navy's final acceptance rate for Hellcats was consistently around 96%. That's incredibly high for a complex machine built at that speed. Compare that to, say, early production runs of the P-38 Lightning, which apparently sometimes had initial rejection rates over 15%. Grumman was building faster and with remarkable quality.
Okay, design proven, production humming. Now the rubber meets the road, or rather, the Hellcat meets the zero in combat. August 1943, the first squadrons are really getting into the thick of it, and the feedback starts coming back.
And this is where Grumman did something pretty radical for the time. They didn't just collect the reports, they acted on them immediately. That pilot feedback loop became essential to the Hellcat's evolution.
You mentioned Lieutenant Commander John Jimmy Flatley's report.
Yeah, Flatley was a highly respected ace, knew what he was talking about. He sent back this detailed 8-page assessment, no punches pulled. He praised the plane's strengths, but was brutally honest about the weaknesses found in actual combat.
Like the aileron control at high speed?
Exactly. He pointed out that above 300 knot speeds, you definitely needed to chase down or escape a zero. The stick forces for rolling the plane became incredibly heavy. The aileron stiffened up, making it really hard to track a maneuvering target accurately.
A potentially fatal flaw in a dogfight.
Absolutely. And Grumman didn't shelve that feedback for the next model. They tackled it right away.
What was the fix?
It was actually quite an elegant aerodynamic solution. They added small spring tabs to the trailing edges of the ailerons. These tabs used the force of the airflow itself to help the pilot move the control surfaces, kind of like power steering, but using aerodynamics.
And that restored precise control at high speeds.
It did, a relatively small modification, but it made a huge difference in combat effectiveness and pilot confidence. Gave them back that fine control when they needed it most.
Flatley also pointed out issues with visibility, didn't he? Blind spots?
Yep. The original canopy structure, while strong, created a nasty blind spot down low around the 4 o'clock position relative to the pilot.
Which is exactly where an enemy fighter might be sneaking up or diving away.
Precisely. Again, a critical issue. You can't fight what you can't see. So Grumman's engineers had to make a tough call balancing structural integrity with pilot vision.
What did they do?
They carefully redesigned the canopy framing, slimmed down one of the structural members, repositioned a strut slightly. It was a compromise, maybe marginally weakening the structure, but it opened up that crucial viewing angle just enough. Again, prioritizing the pilot's ability to fight and survive.
They even address things that sound smaller, like ergonomics, seat height, control placement.
You bet. Because fatigue is a killer in long combat missions. Pilots reported the seat was too low, causing back pain on 8-hour patrols. Sounds minor, but it degrades performance.
The fix.
Simple. They raised the seat mounting by 3 inches. Problem solved. Another one was the flap lever.
Right, for carrier landings.
Yeah, on final approach, you need one hand on the stick, one hand constantly adjusting the throttle for precise speed control as you line up with the deck. The original flap lever position forced the pilot to take his hand off the throttle to adjust flaps. Extremely dangerous at a critical moment.
So they moved it.
Moved it 6 inches closer to the throttle quadrant within easy reach. These seem like tiny tweaks, but they add up. They made the plane fundamentally less stressful and easier to operate under pressure, freeing up the pilot's mental bandwidth to focus on fighting.
But arguably, the biggest change driven by combat feedback was the armor upgrade. This came from intelligence, right? Knowing how the Japanese were adapting.
Exactly. The Japanese pilots weren't stupid. They quickly learned the Hellcat was fast and tough, but they also figured out its vulnerable spot, the underside. The belly armor was relatively thin.
So they changed tactics.
Yeah, they started trying to bait Hellcats into turning fights, then diving underneath for deflection shots, aiming up at the pilot or the wing root fuel tanks. A nasty, effective tactic.
Grumman had to respond. What was the solution?
It was straightforward, but added significant weight. They installed a heavy 212-pound steel armor plate behind the pilot's seat and added more armor plating around the critical fuel tanks in the belly and wing roots.
212 pounds. That must have impacted performance.
It did, slightly. Made the plane a bit heavier, maybe fractionally slower to accelerate or climb. But the trade-off was massive gains in survivability. Pilots who took solid hits from below, which previously might have been fatal, were now making it back.
And crucially, because of that modular design we talked about.
They could phase in this major weight addition, plus the spring tabs, plus the canopy changes, plus the ergonomic tweaks without stopping the production line. That's the real genius here. The Hellcat wasn't static. It was constantly evolving month by month based directly on what pilots were experiencing in the Pacific. It truly was a living weapons system.
Okay, so this constantly refined, rugged, powerful fighter hits the fleet in numbers. And that leads us to perhaps the most famous statistic associated with the F6F Hellcat, the 19-to-1 kill ratio.
19-to-1. It sounds almost mythical, doesn't it? But it's a number borne out by exhaustive post-war analysis, cross-referencing both U.S. Navy and captured Japanese records for air-to-air combat losses.
How does that compare to other fighters of the era? Just to put it in perspective.
It's in a completely different category. The legendary British Spitfire, fighting the Luftwaffe over Europe, achieved maybe a 2-to-1 kill ratio overall. The P-51 Mustang, another icon, probably managed around 3.5-to-1 against German fighters.
So 19-to-1, that's not just superior, that's annihilation.
Pretty much. It represents total dominance in its theater, and a huge part of that came down to the fundamental performance advantages we discussed.
Starting with speed.
Speed is life. The Hellcat, with that supercharged R2800, could hit around 380 mph up high, maybe even touch 400 in a dive. The Zero topped out closer to 330. That 50 mph difference was decisive.
How did pilots use that speed tactically?
It meant the Hellcat pilot almost always controlled the terms of engagement. If a Zero got on his tail, the last thing he wanted to do was get into a low-speed turning fight. The Zero would win that every time with its agility.
So what did they do instead?
Punch the throttle, enter a shallow dive to pick up even more speed, and just extend away. Use that raw speed advantage to open the distance until the Zero was out of gun range and falling behind.
Then use the superior climb rate to get back above them.
Exactly. Climb back up, regain the altitude advantage, and then re-engage on your terms, usually diving down on the Zero. It completely neutralized the Zero's primary strength, its maneuverability, by refusing to play its game.
And this ties back to that core design philosophy difference, durability versus agility.
Absolutely. The Japanese philosophy, epitomized by the Zero, prioritized lightness and maneuverability above all else. That meant sacrificing protection. No pilot armor, no self-sealing fuel tanks. Great for turning, terrible for taking hits.
Whereas the Hellcat
It was built like a Grumman. It carried that 212 pounds of pilot armor, plus additional protection, plus self-sealing fuel tanks that could often absorb hits without igniting. It was designed to take punishment.
What did that mean for the pilots, especially inexperienced ones?
It meant survival rates were dramatically different. A few bullets into a Zero's wing root or engine could turn it into a fireball instantly. An inexperienced Hellcat pilot might get shot up badly, but the plane's sheer toughness often allowed them to disengage, limp back to the carrier, and survive.
There are incredible stories of Hellcats landing with huge chunks missing.
Oh, yeah. Photos of planes with half a wing panel gone, engine cylinders shot out, control surfaces shredded, yet the pilot walked away. That ruggedness built immense confidence. Pilots knew their plane could take a beating and still bring them home.
We also can't forget the hitting power, the armament.
Critically important. The Hellcat carried 6 Browning M2.50 caliber machine guns, 3 in each wing. These weren't rifle caliber guns. These were heavy machine guns firing explosive or incendiary rounds.
And a lot of them.
400 rounds per gun for a total of 1,400 rounds. When the pilot squeezed the trigger, all 6 guns fired simultaneously.
What's the rate of fire on that?
It works out to about 4,800 rounds per minute combined. That's 80 50 caliber slugs heading towards the target every second.
80 bullets a second.
Yeah. Against a lightly built plane like the Zero, the effect was devastating. Pilots described kills as lighting matches, or the Zero simply disintegrating. A short, well-aimed burst was usually enough.
So superior speed, ruggedness, and overwhelming firepower. But there was also a key tactical element, wasn't there? The THAC weave.
Yes, doctrine played a huge role. Developed by Commander John Thatch early in the war when flying Wildcats, it became standard practice for Hellcat squadrons. It transformed how fighters supported each other.
How did it work?
Basically, 2 Hellcats would fly parallel, maybe a couple hundred yards apart, acting as a team. If an enemy fighter attacked one of them, let's say both the leader and his wingman would immediately turn towards each other, crossing paths.
Okay, so they turned to the attack.
Exactly. Now, the attacking Zero pilot, who was focused on his initial target, is suddenly faced with a choice. He can either follow his target through the turn, which flies him directly into the gun sight of the other oncoming Hellcat.
Or he has to break off the attack completely.
Right. It forces the attacker onto the defensive. It turned the Zero's maneuverability against itself by presenting an inescapable threat from the wingman. It countered the more individualistic, samurai-style dogfighting tactics favored by many Japanese pilots.
So it was teamwork, combined with the Hellcat's strengths, that made the difference.
Absolutely. The THAC weave, flown religiously by disciplined Hellcat squadrons, maximized the plane's advantages and systematically dismantled the Zero's strengths. That's how you get to 19-1.
There's one battle that perfectly encapsulates this Hellcat dominance. It even has a grimly famous name, the Great Marianas Turkey Shoot, June 19th, 1944.
Yeah, this was it. The Japanese Navy threw everything they had left in terms of carrier air power into one massive, desperate gamble to stop the U.S. invasion of the Mariana Islands, particularly Saipan.
How big was the Japanese attack force?
They launched 373 carrier aircraft Zeros, Val dive bombers, Kate torpedo planes, a huge wave.
And what met them?
About 450 F6F Hellcats flying combat air patrol off the U.S. carriers, ready and waiting. Many of them flying in those disciplined THAC weave formations.
The result wasn't really a battle, was it?
It was a slaughter, an industrial-scale destruction of Japanese naval aviation. The Hellcats just tore into the incoming waves. The Japanese pilots, many of them less experienced by this point in the war, flying planes that were now significantly outperformed, stood little chance.
What were the final numbers for that single day?
They are staggering. The Japanese lost around 330 aircraft shot down. American losses, just 23 Hellcats in air-to-air combat.
A 14-to-1 ratio in one day's fighting.
Yes. It effectively broke the back of Japanese carrier aviation. They lost hundreds of planes and, more importantly, hundreds of experienced pilots they simply could not replace. They never seriously contested air superiority at sea again after that day.
And this highlights the other crucial factor, the industrial mismatch.
Absolutely. Every one of those 23 Hellcats lost in the Turkey shoot could, in theory, be replaced by a new one rolling off the Bethpage line within about a week or two at that point.
Japan had no hope of matching that.
None whatsoever. Their aircraft production was strained, resource-starved, and couldn't keep up with losses, let alone match the sheer volume the U.S. was producing. Remember, Grumman alone built nearly 6,400 Hellcats in 1944. Japan's total aircraft production of all types that year was only about 28,000.
So the Hellcat didn't just win battles, it won through attrition, backed by overwhelming production.
It created an aerial shield. That dominance in the air allowed the U.S. Navy and Marines to conduct amphibious landings, Tarawa, Kwajalein, Saipan, Iwo Jima, Okinawa, with relative impunity from enemy air attack.
Which must have significantly impacted planning and casualties on the ground.
Immensely. Knowing that the fleet and the landing forces were protected from large-scale air raids, simplified logistics, boosted morale, and undoubtedly saved thousands of lives during those brutal island assaults. The Hellcat provided the essential air superiority umbrella that made the entire island-hopping strategy viable.
But even as the Hellcat reached its zenith, its time was already running out, technologically speaking.
The pace of change was incredible back then. By the war's end, in August 1945, Grumman had built a total of 12,275 F6Fs. An amazing number. But the jet age was dawning.
The Navy was already looking past propellers.
Oh yes, they were already testing hybrid prop jet fighters like the Ryan FR-1 Fireball right after VJ Day. And the first pure carrier jets like the McDonnell FH Phantom were entering service by 1947. These planes were pushing speeds 150 mph faster than the Hellcat could manage.
So the Hellcat had a relatively short, though incredibly impactful, frontline career.
Very short. First flight in 42, largely retired from frontline duty by the early 50s, officially retired by 54. Just 12 years from maiden flight to museum piece, basically. But its impact during those critical years was immeasurable.
So if the plane itself became obsolete relatively quickly, what's its lasting legacy?
I'd argue it's not the airframe itself, but the philosophy it embodied and proved successful. The Grumman Ironworks approach. Rugged simplicity, designing for manufacturability, designing for repairability, and above all, focusing relentlessly on the pilot's needs and survival.
That became Grumman doctrine.
It really did. You can draw a direct line from the Hellcat's design principles, especially that focus on maintenance by ordinary sailors on a carrier deck, straight through to later Grumman legends like the F-14 Tomcat in the 1970s.
Keep it tough, keep it fixable, keep the pilot safe.
That's the core Grumman legacy forged in the Hellcat program. And beyond the hardware, there's the human legacy. You just can't quantify it, but think about the thousands upon thousands of pilots who came home because they were flying a Hellcat.
Pilots who survived damage that would have doomed them in another aircraft. Exactly. They survived, came back, contributed to post-war America. That survivability, built into the plane's DNA, had a profound human impact that echoes down the generations.
So maybe the Hellcat wasn't the absolute fastest or the most agile or the most technologically advanced fighter of the war overall.
Probably not on paper, no.
But for those critical 16 months of development and the crucial years of combat that followed, it was exactly the right plane, built the right way, delivered at exactly the right time. Sometimes that's what makes history. Perfect timing, perfect execution.
And that execution really boils down to those key takeaways we've discussed. First, that ruthless Grumman commitment to simplicity and manufacturability, making every rivet count. Second, that incredibly rapid real-time integration of combat feedback, thanks to the modular design. Pilot spoke, Grumman listened, and the plane got better. Fast.
And third, the sheer power of American industry, focused like a laser beam, building these rugged machines with surprising quality control. Which really leaves us with a fascinating question, doesn't it? A final thought for you to ponder. When you look at modern defense projects today, incredibly complex systems like, say, the F-35 fighter that often face development timelines stretching decades and persistent production challenges.
Yeah.
What can we still learn from the F6F Hellcat story? A plane that went from urgent requirement to mass-produced, war-winning reality in just 16 months, built largely by people who were new to factory work entirely.
Did Grumman prove back then that speed, simplicity, and quality aren't mutually exclusive? That maybe prioritizing ruggedness and the user's needs from day one is a faster path than striving for ultimate complexity?
It makes you wonder if sometimes, in our quest for the most advanced technology possible, we lose sight of the power of simple, robust engineering delivered quickly and reliably. Something to think about until our next deep dive.